Good evening, everyone. Welcome to our May lecture. We're so glad that you're here. I want to first thank our sponsor, Enterprise Bank and Trust. They have provided for our season, our 25-26 season. We will take a break after tonight's lecture, and we will begin again in September. But tonight, I am very excited to welcome Dr. Ralph Hollis to Fuller Lodge. Dr. Hollis's memoir, Countdown to Launch, Rockets, Computers, and Coming of Age in the Cold War. He'll be signing books afterwards. And this memoir explores his passion and perseverance and love of rockets and computers that eventually led to his work on Minutemen 3. We look forward to learning more about these in his talk tonight, so please give a warm welcome to Dr. Ralph Hollis.
Well, thank you, Rachel. Thank you very much. It's such an honor to give a talk here, such a hallowed place in history. Los Alamos and this building, in fact, is fantastic. I'm going to do a little audience questioning here. How many of you have seen the Oppenheimer movie? Everybody? Okay. If you haven't, we've seen it twice. We're going for a third time here. So how many of you know about Minutemen 3? Quite a few, actually. Yeah. Okay, that's cool. I want to tell a little bit about myself and sort of get around to why I wrote the book. And I want to tell you a lot about Minutemen and so on and so forth. So I'm a stranger here, actually, but I have connections to Los Alamos in a way. Between the ages of 1 and 2, I lived in an adobe house in Santa Fe, where my young architect father worked for a company called Kruger and Clark Architects. Kruger and Clark built many of the buildings in the early part of Los Alamos, and they were, for a while, at least according to ChatGPT, were the sole architects at the very beginning. Later we moved to Fort Worth, Texas, then Salina, Kansas, and then Wichita. So my father worked at Boeing Airplane Company in Wichita, Kansas, and then worked in Hanford, Washington, which is another place I'm sure you all know about. He never talked about any of these things, so I'm not sure what he worked on exactly. Okay. I do have some other connections to here. Later on in my life and my career, I worked on a microassembly project with Sandia, just down the road here, over in Albuquerque. So those are my connections, and I want to tell you about Minutemen 3, and I want to go into some details. I promise there will be no equations. Okay, so let's see if this is going to work here. Right now, as I speak, there are roughly 400 Minutemen 3 intercontinental ballistic missiles in the U.S., and they're ready to launch in about 10 minutes' time by command from the President of the United States, which is kind of a scary thing to think about. So I want to explain how the guidance system works. How does a Minuteman 3 get from a launch point to a target? How does it do that? Okay, very few people, nobody knows about it in the public, generally speaking. So I want to tell about that. Then I want to go back in time some 70 years to tell about how I got interested in rockets and computers that led to working on Minuteman 3, okay, a lot of years ago. I want to mention a heartbreaking event that happened in my life, which ironically set me up to work on Minuteman 3. Then I will tell you about a computer program that I helped write called the Minuteman Flight Simulator. It calculated the flight of the missile in a virtual simulation of the missile in great detail. And finally, at the end, I want to have an audience participation event, I think, So I'm going to ask you some questions. So pay attention. Okay. So, all right. So I want to play this video that's on the screen right now. And I want to show you exactly where all 400 of these Minuteman III missiles are, because nobody else knows it. Okay, really, I mean, but here we go. So we're going to zoom in on Google Earth Studio, and we're going to go to find some launch control facilities. There's one, and that happens to be in Montana. There are launch control facilities that are manned by the missileers, 2 at a time. Each one is controls 10 launch facilities. Each launch facility has a Minuteman III missile right now, okay, as we speak. This is not history, this is right now. So if we go over towards North Dakota, there's one of the launch facilities right there, has a Minuteman III inside. And these sites surround Minot, North Dakota, which is the city, you can't see it, it's right in the middle there. That's Minot. Okay, we're going to go down now to Wyoming, and we're going to go see another launch facility here, right there. And then we're going to zoom out, and those are all the sites around Wyoming, but also in Nebraska and in Colorado, some in Colorado. So, okay, so I want to tell about the Minuteman III missile. It looks like this. It's pretty big, not so big, but pretty big. This shows all the contractors that built the various pieces of the missile. Each of the 3 solid propellant stages burn for about 60 seconds. The bottom stage, the first stage here, has steerable nozzles. The other stages, 2 and 3, have liquid injected thrust vector control. And stage 2, the freon is injected into the exhaust, causing a shock wave which deflects the exhaust, and that's how it can steer, with a single nozzle. Very clever. In the third stage, they use strontium perchlorate instead of freon. I'm not sure why. There's a liquid fuel fourth stage by Bell Aircraft, that purple thing. And that can run for about 6 minutes duration, so the total flight time of about 9 minutes of powered flight. That stage has liquid propellants, hypergolic propellants, monomethyl hydrazine and dinitrogen tetroxide as an oxidizer. And it has an axial engine and 10 small thruster engines for steering. So originally, the Minuteman III, of course, it's the latest of 3 Minuteman series, of Minuteman I, Minuteman II, Minuteman III. Minuteman III is the only one we have today. And Minuteman III makes up 1/3 of this so-called strategic triad. We have the Minuteman III land-based missiles, we have the submarine-launched ballistic missiles, and we have the bomber force. So it's an important part of the whole scheme. So originally we had 3 Mark 12 RVs with W-62 warheads, yielding about 170 kilotons each, about 11 times that of the Hiroshima explosion. Then they were moved to Mark 12A RVs with W-78 warheads, yielding about 330 kilotons each, 22 times the explosive power of the little boy bomb on Hiroshima. And there's a Mark 12A in the museum, so you can see that. 30 years ago, I visited Hiroshima and with my 10-year-old son, and it's a horrendous thing to see. I visited the atomic city. So Minuteman III was the first implementation of MIRV, M-I-R-V, followed by the Soviet Union 5 years later. So MIRV means multiple multiple independently targetable reentry vehicles. Each reentry vehicle has a nuclear warhead, thermonuclear warhead. So, yes, 5 years later, the Soviet Union caught up with us. Okay, so it was quite a delay for the Soviet Union. So we're going to take a look at some of the parts here. That's the post-boost propulsion system. And you can see the axial engine and the two tanks, the fuel tank and the oxidizer tank. Located above that is the post-boost control system. That's, I had a good deal to work with that, although I never saw one in actuality, until I saw one in the Air and Space Museum in Washington, D.C. So that's the post-boost control system. We'll get into that. And then the MERV payload at the top. Okay. Since the Obama administration, that's been downgraded to a single Mark 12A instead of a triple warhead. Okay, but they can all be upgraded back to triple if we need to have them that way. Okay, so I want to talk again, like, how does it get from the launch site to the target? So what you have to understand there is the thing called the reference trajectory. So it's a smooth curve, and I'm going to throw one little piece of geometry to you. That's the launch-centered Earth-fixed coordinate frame down at the bottom. And when the missile is in its silo, it's pointing straight up, really straight up. And the z-axis of this coordinate frame is straight up against gravity. When the missile takes off, it pitches over in the pitch plane of the reference trajectory, shown here. But the missile, as far as the missile knows, it keeps exactly the same coordinate frame as it's flying, as it had at the beginning. We'll see how that happens. So each part of the powered flight goes on until this point. And the deployment of the reentry vehicles has to be extremely precise. If it's a little bit low velocity, it'll hit, without hitting, it'll hit shy of the target. And if it's more, if it's, anyway, the range depends on the time of cutoff. Okay, so each point of this trajectory has two main coordinate numbers associated with it. One is the attitude of the rocket, the missile, with respect to the launch-centered Earth-fixed coordinate system, and the other is the velocity. Okay, so doing the reference trajectory requires precise knowledge of both the launch and target locations. Only the powered portion is controllable, and it's not so easy because the Earth is not a sphere. It's 27 miles fatter at the equator than it is pole to pole. And also, the gravity of the Earth is rather bumpy. There are mountains and there are valleys and oceans and so forth. All of those things change the path of the missile, both during powered flight and after the payloads are released, all the way to the target. So calculating this reference trajectory is a hard problem that actually starts with the target and works backward to the cutoff point. This is how it is calculated. There's an iterative physics solution as well, and it uses a gravity model of the Earth that's been obtained from many observations of Earth satellites flying over. So this is the post-boost control system. What I call the heart of the missile is the gyro-stabilized platform at the top. And the brain of the missile is the D-37D computer, which was replaced in 2007 by a Honeywell computer. So the first D-37 was built by Autonetics Division of North American Aviation. So the D-37D had 14,024-bit words. Half of them are used by the ground program, so that only leaves 7,000 words of code to put together the program that flies the missile all the way there. So it's not much memory. There are also high-speed loops, which put the data many times around the rotating disk memory. The main memory is operating at 6,000 RPM. These high-speed loops cause the latency of the spinning disk to be reduced quite a bit. So there's a H loop, and that's the commands to steer the missile. There's a V loop, which has velocity input from the so-called PIGAs. I'll talk about those. And R loop is resolvers coming from the gimbals of the inertial measuring unit. The D loop controls the post-boost propulsion system thrusters. And the U loop is a fine countdown timer, for making the release of the warhead very precise. And the D-37D used pioneering integrated circuits from Texas Instruments. And the advances in integrated circuits from building that D-37D permeated the entire future of integrated circuits in the United States. So that was a very pioneering thing that Texas Instruments did. Okay, so this is a little closer look at the inertial measuring unit here. There are two main gyros that stabilize this platform, and there's 3-axis gimbaling. So these circular parts can rotate, and they're the gimbals holding the stable platform, which is in the center. Now, there's also a true north-seeking gyro compass that points north, true north, within a few tenths of a degree actually from the star Polaris, north star. And there are 3 of these pendulous integrating gyro accelerometers, which I will explain to you in a few moments. The PIGA is what gives the Minuteman III and similar missiles its real accuracy. It was first invented by Dr. Fritz Mueller for the German V2 rocket, then refined by the MIT Charles Stark Draper Laboratory, and then it was refined further by the Autonautics Division of North American Aviation, where I worked. And then Honeywell and AC Sparkplug Company made them in quantity. Okay, so altogether in the nose of the missile, there are 7 spinning masses supported on hydrogen gas bearings. Imagine that. And that was in 1970, and it's the same thing now. Right now, as we're talking, there are 400 of these IMUs out there. They're all spinning masses, 7 spinning masses on hydrogen bearings, and they can operate for months at a time without any problems. Okay. So this is a little diagram of the stable platform, what we saw before, with the gyro compass and the 3 PIGAs that are right here, pendulous integrating gyro accelerometers. There are electrochemical level sensors that try to find the vertical to make sure it's up and down. This is up and down, really, the plumb bob vertical, essentially. And torquers keep the stable platform level as the Earth rotates. Without the torquers in these gimbals, in the pink gimbal and the purple gimbal, this stable platform would not be stable. It would rotate 15 degrees per hour as the Earth rotates. So these torquers keep the platform level at the launch site as the Earth rotates. That's very important. And that's executed by the ground program. When the missile takes off, the same torques are applied. So that means the Launch Center Earth Fixed Coordinate System stays fixed with respect to the missile, exactly like I showed in the reference trajectory. So these PIGAs are a real work of art. They're highly miniaturized, smaller than a small juice can. The gyro compass rotor is constrained to be in the local horizontal, and within a few arc seconds finds true north. True north would be if you could stand at the North Pole and look straight up. That would be true north. So that's what, it's right along the axis of the rotating Earth. So there's an autonetics engineer, senior engineer named J.M. Worth, who said aligning the IMU platform is like threading a needle from 400 feet away or kicking a field goal from 50 miles away. That's how accurate this thing is. I mean, it's absolutely amazing. And the pigas don't measure acceleration, they measure velocity. How can something like that measure velocity? How can that be? So I want to take you through that. Again, no equations, but this is a gyroscope that should be turning. Toy gyroscope, okay. Now the rate that that gyroscope is turning is proportional to gravity, okay. If you would put one of these in the nose of a missile, the missile takes off, it would rotate faster because it would respond to the gravity of the Earth plus the acceleration due to gravity, acceleration of the missile. So directly proportional to that. So here's a picture of what I would call a crude accelerometer. There's this pink frame, and there's a mass screwed onto it, and a pivot, and a spring that balances it. Now, if the missile takes off, you can kind of see that because of this off-centered mass, this the pointer on the scale is going to go down, and so that's how you can measure acceleration in a crude way. To improve on that, you can put a torque motor on that axis with that off-centered mass. And now, no matter what the acceleration of the missile is, the idea is to keep the pointer at 0. Okay, so that's a servo accelerometer. Now, if we, and by the way, on these previous things, the gray part is attached to the rocket. The rest of it is pivoting. So here, if we make the whole thing be able to move around an axis, and we replace that mass but with a motor and a rotating mass, we have a gyroscope there, then the entire system can precess at a rate proportional to the acceleration, just like the toy gyroscope. If, however, we add an additional torquer at the bottom, this yellow-colored torquer, and we put just enough torque there to keep the whole thing from precessing, then we have a PIGA, a pendulous integrating gyro accelerometer. So on stage 1, as I say, with the same torque applied, the green part will start precessing at a rate proportional to the missile's acceleration and not to gravity. So and the total angle of the green part then is proportional to the velocity of the rocket. So of course we have 3 of these PIGAs in the nose of the rocket, and so it's measuring, with those 3 things we can measure the velocity very precisely by the physics of how this precession works. So the PIGAs are all over 60 years old. 1,200 of them are out there in 400 missiles. Each one is 1.6 inches in diameter, for example. So how do I come to know this stuff? What are my connections to Minuteman 3? Okay, that's what I want to go through next. So going back 70 years, I'll show you what got me started in rockets and computers. So I was a kid, a middle school student. This is my teacher, Joe Foraker, on the left. And I entered a contest called the Future Scientists of America Foundation. And I had read in a magazine, or seen in a magazine, a model of an Earth satellite, which was a model by S. Fred Singers. He called it the MOUSE, Minimum Orbital Unmanned Satellite of Earth, MOUSE. So I made a model like the magazine picture that I saw, out of a juice can and a bunch of random electronic parts laying around. Then I wanted to build a rocket, so that's down below here, to just demonstrate the principles of rocket propulsion. And of course, at that point, which was 2 years before Sputnik, no rocket had ever launched anything into space at that point. It was 5 years before you could buy Estes model rockets, which maybe some of you have played with. So my rocket was a failure, bad failure. Not to be, it was, I should have thought it would be a failure, and it was. But I wrote it up, sent it into Washington, D.C., to the Future Scientists of America Foundation, and I got the first prize in a 6-state region. I got my picture in the paper. And I thought, well, I'm maybe getting a little bit famous. So I kept going. Even though I had won the contest, during that summer, I built 2 more Vulcan rockets, Vulcan 2 and Vulcan 3. They were both failures. I tried to improve on each one, but they all failed miserably. So at the end of the summer, I had failure, failure, and failure. And at the end of the 3rd failure, that same evening, I tried Vulcan 3, the Soviets launched Sputnik 1. So that was quite a thing. So, well, we wanted to, we knew at that point there were several other people building rockets around the country. You know, we see newspaper articles of kids that blew their hands off and stuff. We were extremely careful with everything, using electrical ignition and all that stuff. We wanted to be a little more scientific than everybody else in the country, right? So we had the ego to say, we want to calculate the flight of the rocket. We wanted to simulate it using a digital computer. So this was my senior year in high school, 1959. But at the local University of Wichita, there was an IBM 610 there. So I started to go to the university, and I started calculating the flight of our rockets using this IBM 610, which had decimal arithmetic, vacuum tubes, rotating disk memory, all of that. And at some point, they took the IBM 610 away, much to my dismay. At that point, I had more hours in the logbook than anybody else, any of the faculty or the graduate students there, and I was just a senior in high school. But soon after that, they brought another computer in, the Bendix G15. Again, it was decimal arithmetic, vacuum tubes, rotating drum memory, and all that. So I continued to work on the G15. I learned the Intercom 500 language for the G15, and really was going good. And then they took the G15 away because it was just a demo, you know, that the university didn't really want to buy. However, and both of these computers, that's what they used for input and output, 8-channel punched paper tape, okay? So after the G15 disappeared from the university, I got a special pass to go after midnight to the Beach Aircraft Company in Wichita after midnight, and they had 2 Bendix G15s. And I could bring my paper tape from University of Wichita and put it in their G15s, and I could continue my calculations of rockets. So that was incredible. At the time, though, I was transitioning to being a math major at the University of Wichita. And I was taking differential equations and taking complex variables, a 9 o'clock complex variables class, and I would work from like midnight to 3 a.m. in the morning at Beach Aircraft Corporation, and then I would try to go to my class and do my homework. And my math grades were just awful. They really got bad, so I thought maybe that was the end of the road. So during this time, let me just point out, life was very tense around the country, but also in Wichita. Wichita had Boeing Airplane Company. They just built B-29s there in the 1940s. They transitioned to B-47s, B-52s, and so it was a Soviet target of Soviet airplanes and missiles, without a doubt. So then a little bit later, in 1962, they surrounded Wichita with 18 Titan II missiles, which made it even more of a target. So it was really amazing. But anyway, so we started thinking about building bigger rockets and launching them, things like this. And again, calculating the rocket's flight with the computer. So this is our cryolite two-stage rocket. We broke into a machine company after midnight and commandeered a lathe to machine the nozzles for this cryolite two-stage rocket. And the calculations that I performed on the computer at Beech Aircraft Corporation indicated that the rocket would have about a 35,000 foot altitude capability, which at the time we thought was possibly an amateur altitude record. So, and here's another view of the cryolite staging here. So, suddenly my life changed considerably. Suddenly my girlfriend got pregnant. Okay. We married and we moved to Manhattan, Kansas, where I entered Kansas State University at age 19. So later we had a daughter and another daughter, 2 years after that. But this was the end of my amateur rocketry, basically. So Manhattan Project operator, person, A.B. Cardwell, convinced me to switch from math to physics. And so I did. I switched from math to physics. I struggled. I took advanced mechanics, got an F in advanced mechanics. Okay, F equals MA, right? But it's more complicated than that. But a year later, I took the course again, and I got an A at that time. So that was good. So I finally wound up with a bachelor's degree in physics and then a master's degree in physics. I did crystal structure analysis on the computer, and I learned Fortran too, programming there. So that was very important. So I started work on my PhD. Turns out I was an experimental physicist, and the experimental physicist had to pass a big exam in order to be let on to get a PhD. Okay. So I passed the exam, but my good friend, Rocky, failed it. So he didn't go on for his PhD. He went off to California to work for North American Aviation, Autonetics division. And so I was taking advanced quantum mechanics. I failed the midterm completely. I couldn't get my mind off of it because my wife had left me with my girls. I didn't even know where she was. And I could not concentrate on physics anymore. So I went out to California, and that's when I started working for Autonetics. I thought I had 3 more years and I'd have a PhD in physics from Kansas State University. But with 2 kids and stuck at home and all that, I think my wife was just not up to it, going through all that for and the lack of money and everything else for 3 more years. So my rocketry was interrupted. This is my wife, my former wife, Adine, my daughters, Carol and Dana. But 2 of my fellow grad students earned their PhD in physics and wound up right here at the Los Alamos National Lab. And one of them is Don Burton, right there. Don, put up your hand. And another was the late Phil Reinard. I don't know if Carol is here, his wife. I guess not. But anyway, they were both lifetime employees at LANL. So, yeah. Okay, so let's go on. So what I did there at Autonetics was I built this computer program that simulated the flight of the missiles, of the Minutemen missile. Before I did that, I worked on at-sea gravity measurements, ring laser gyros, and eventually Minuteman III. So we had a big meeting with the big boss, and there were a number of people, about a dozen people, and he announced that Autonetics was going to work on a new missile called Minuteman III. And it was going to be like Minuteman II with 3 solid propellant stages, but it was going to have a 4th stage. The 4th stage was liquid fuel. And they had an analog simulation of Minuteman I and Minuteman II using operational amplifiers with vacuum tubes and so forth, but they didn't think it would do the job for Minuteman III. So the boss asked, he said, we need to make a digital flight simulator for Minuteman III. And would anybody like to take that job on? And there was no response around the room, and I kind of put my hand up. I said, well, I mean, 6 years ago, I calculated the flights of my rockets using early digital computers. And he asked, what computers did you use? And I said, IBM 610 and Bendix G15. Well, I told him about the rockets that we had underway and all that. And 3 days later, he asked if I wanted to do it. He said, you want to build this flight simulator? And I thought about it, and I thought, well, if I turn it down, my job at Autonetics would be gone forever. If I did it, it could be a failure. But anyway, I decided to do it. So this is how the Minuteman flight simulator works in general. Okay. It's implemented inside of a Model 65 IBM 360 computer, which was brand new at that time. And the first thing we had to simulate was the operation of the D37D onboard computer. So we had to simulate all of its instructions. It had 24-bit instructions that were embedded in the 32-bit System 360 instructions. And it had to accurately simulate the rotating disk main memory of the D37D and many other things, all the inputs and outputs and so forth. And there were 2 main inputs. One is the reference trajectory, which I taught you about earlier in the talk, and the flight program written by the flight programmers there. It also had outputs. Many explosive devices go off when the Minuteman launches. Staging and tons of stuff go off. And there's also analog outputs that control, like the liquid injectant thrust vector control and the first stage nozzles and all that. So there's a lot of outputs. That's represented by the arrow that's going off to the right. But the one thing it does constantly is it talks back and forth with the IMU model. So we had to model all the mathematics of the inertial measuring unit and the operation of the inertial measuring unit in a tremendous amount of detail. So the first thing in the missile that we needed to look at is a model of all the actuators. There's a lot of actuators. We had to model all of those, and they each have a detailed response function. Those affected the airframe of the rocket. We had to have a propulsion and structure model. And there's arrows connecting all of these things, which I'm not going to show here. But we also needed to take into account the temperature, especially for the first 3 stages. The solid propellant stages are vastly sensitive to the temperature of the propellant. Okay, so if it's hot, it burns really fast. If it's cold, like up in Minot, North Dakota, it's going to burn slow. So that's a variable that we cannot, calculate really, but we can look at the ins and outs of that temperature range. Well, all of that goes into a translational model of the rocket, the sort of the X, Y, Z position of the rocket with respect to the Earth. Of course, as I mentioned before, that requires a detailed gravity model. The model we used was a very highly secret model, the eighth order spherical harmonic expansion of the Earth's gravity. And of course, we had to simulate the rotational motion of the rocket as well. So that meant we had to simulate the atmosphere. So we had an atmosphere model. And we had to simulate wind profiles that the rocket is flying through. And all this is to get the bomb to the target. You guys do a great job of building the bomb, but somehow we had to get it there. So we had to simulate all of these things. So we had an aerodynamic characteristics model as well. So altogether, Minuteman Flight Simulator solves 54 simultaneous ordinary differential equations. So this is where I worked in Autonetics in California. There were 20 buildings at this peak in employment. We had 36,000 workers. It was the nation's largest military electronics complex. We had many 80-hour work weeks of intense pressure. Many obstacles and setbacks are described in my book as we went along trying to get this thing to work. At that point, in the 1968 time form, 67 time form, Soviet Union was building large numbers of hardened silos and getting development of anti-ballistic missile systems that could defeat Minuteman I and II. The government felt that it could. So this thing was on Clark Clifford's blackboard. Clark Clifford was the Secretary of Defense. We felt the pressure coming down on my management and down to personally me, and intensely. So a lot of that is described in my book. So now it's time for the quiz. Okay, if everybody can wake up briefly. I have some characters that have some Los Alamos history that I want to show you. And I got to meet some of these people. So I'm going to put them on the screen. Anybody recognize this character? No, nobody? Okay, this is Richard Hamming. He worked with Feynman and some of those people, Richard Hamming, sorry. I have a story to tell. I promised some of the people here that I'd tell this story to Todd and Rachel. I don't know if they're in here or not, but anyway. In about 1962, I had my friend, Greg Hopwood, had us over for dinner. And so in his apartment in Irvine, California. And so we had a nice dinner, and there was an elderly gentleman there. It was Richard Hamming, who Hamming developed error-correcting codes back in the 40s that really made the internet and disk drives and everything possible, because if you dropped out bits, it could restore the message that was going through. So extremely important. So anyway, we were talking at the dinner, and he said, "You're from Kansas, right?" I said, "Yeah." He said, "Well, I can tell you a story." He was telling us some stories at dinner about Los Alamos. So he said, "Okay, well, after he finished his work at Los Alamos in 1946, he had to drive back to New Jersey to Bell Labs, where he was employed. So he needed a car, or he didn't want to take the train or something. So he bought the car from his colleague there, a theoretical physicist named Klaus Fuchs. So, Feynman had borrowed Fuchs' car many times to go visit his dying wife, down in Santa Fe. So it was, near as I can tell, a pretty battered up blue Buick. But anyway, he said on the way back home, he was driving through the flatlands of Kansas when suddenly the police pulled him over, and the federal agents were there, and they stopped the car and they tore the car apart looking for something. He had no idea what they were looking for. Okay, so that's an original story. You're not going to find it on the internet or anywhere. Okay, so that's it. So that's Richard Hamming. Okay, second illuminant. Everybody knows him, right? Anybody want to say? Ullum, exactly. So Stanislaw Ullum was a professor at the University of Colorado, where I did later get my PhD. I knew he was part of the, he worked with Teller, for the Teller-Ullum architecture of the thermonuclear bomb. I knew about that, but But he also invented, he also, sorry, he also invented a form of mathematics called cellular automata. And I was very interested in that, and I actually wound up building some cellular automata out of integrated circuits, which could display results on a television screen and so forth. So that's kind of my connection, as little as it is, with Stanislaw Ulam. Okay, the third person. Who? Richard Garwin. So I worked at IBM for like 19 years in New York. Dick had his office just down the hall from mine, so I got to know him. I knew he was had worked in Los Alamos or something, but anyway, I later realized he built the Ivy Mike explosion down out in the Pacific. So that's pretty amazing. He just passed away. I was going to send him a copy of my book. I didn't send it in time. But anyway, yeah, at IBM he had invented a markup language for sort of like LaTeX language, which you could write really all kinds of scientific papers, and you could use it as markup language. So I used his markup language, and when I had problems, I would talk to him about it. So anyway, now I want to do one more slide and then a couple more, and we'll finish up. I have a pyramid model of Minuteman 3. So at the bottom of this pyramid, I visualize the launch control facilities, the launch facilities, construction and maintenance requires a workforce of over 10,000 people, today, and just ongoing, okay. Above that, you can count the rocket stages, the reentry vehicles, requiring at least several thousand people to develop, manufacture, and maintain. And of course, each one of those, if they're not dumping warheads, they have some serious bomb inside. Above that is the Autonetics onboard computer and the inertial measuring unit, carefully assembled by hand by perhaps 1,000 people. And that's the company I was working for. And at the top of the pyramid, so-called the spear of the point of the spear, are the flight programmers and the Minuteman flight simulator to verify the flight program's correctness. Okay, so what's amazing is I'm going to show you who these people are. I'm going to enumerate them, in fact. There's the flight programmers, right there. They were run by a guy named John Sweet, 6 of them. They wrote the flight program, the operational flight program for 1,000 Minuteman III missile projected deployment. The Minuteman flight simulator, again, six of us worked to create the Minuteman flight simulator. So it takes very few people dealing with the software stuff, but the entire missile operates on software. Everything is in software. So the irony is, I'll show you in the next slide, it turns out the Minuteman flight simulator became the sole means of verifying the flight program's correctness. So that's what the taxpayers' money paid for, 8-channel punch tape. That's what I started out with the IBM 610. Only this time it's Mylar tape, so it doesn't tear quite as much. But these tapes, in the initial versions, got read into the missiles. They would fly the tapes to wherever the missiles were being tested, like Florida or Vandenberg, and then just read them into the missile. So, okay, now I'm going to play a video. It's going to be a little loud. I hope it works out okay. stage. Okay, third stage blows out, and that leaves the post-boost vehicle with its liquid fuel thrusters. Now, in order to deploy the RV, it has to pitch almost straight down. And after the RV is deployed, it has to back away. Apology for all the weird music, but anyway. So there is no autonetics anymore. There is no autonetics anymore. There's a monument there. So these 36,000 people, some of them got absorbed into Boeing and so forth. But this monument is quite nice at the site of autonetics, pioneering innovations in electronics, guidance, navigation, and control that charted new frontiers on Earth and beyond. So that's my last slide, but I have to tell you a little bit about how I feel about this. How do I feel about my little part in creating a weapon of mass destruction? And it's bothered me off and on through all these years. So I don't know how to deal with it exactly. But in fact, we haven't had World War III so far. So I feel really good about that. Thank you very much. Hi, Todd. Yeah.
So thank you very much. Let's give it up for him one more time. We're going to go ahead and open it up for questions. I'm going to grab another microphone here.
Yeah. Yes. Yeah, you. Pink shirt.
Are any Minuteman parts being built now to replenish old ones?
Yes, I forgot to mention that the new missile that's being built called Sentinel is going to replace all the Minuteman IIIs. It's scheduled to start going online in 2030. That's never going to happen. Maybe by 2040. It's right now running up to $140 billion. The GAO is saying it's a little expensive. Maybe we should think about something else, like fixing up the old Minuteman III. So, yeah, so it's in the plans.
So I have two questions.
Yes?
First, we have these 400 of these 70-year-old missiles sitting around. Can you say something about the testing program?
Yeah, well, every now and then, 2 or 3 times a year, they sort of randomly pull a missile out of a silo somewhere, out of one of these 400 silos I showed you, and they take it to Vandenberg Air Force Base and launch it. Most of the time it works well. Now the missiles do need maintenance, like they will run it months at a time, but you know, a bearing will get kind of fucked up, you know, whatever. And so it has to go, they have to pull parts out and change it and stuff a lot. So there's a lot of people maintaining it. Also the silos are, you know, these underground silos, 12-foot diameter tubes that go way down in the earth. There's water down there, there's rust and, you know, steel lined concrete, rust and everything. So anyway, those are all problems, but they are tested, yes, definitely tested.
Second question. Clearly you didn't cease working when you left Minuteman III. Can you say something about your life since then?
Oh, well, thanks, Don. Well, my life's been interesting. So after getting my PhD at University of Colorado, I went to Paris, France for a while, worked at the University of Paris on physics. And then I went to IBM Research in New York. I spent about, 17 years working for IBM Research in Yorktown Heights. And in the mid part of that, I stopped working on physics. And I threw that all away, and I decided to take up robotics instead. So I worked on a robotic mechanism, and I used basic physical principles, like F equals ma, like advanced mechanics and stuff. I used those to build devices for automation, for IBM, and human-computer interaction devices and so forth. And then after that, went to Carnegie Mellon University in Pittsburgh, where I am now. I've been at Carnegie Mellon now for 33 years. I'm a so-called emeritus professor, so it means part-time. I get half-price parking there. And it's been great. At the University of Colorado, I met a lady. Her name was Beth. We got married. We had two boys. So I had 2 daughters by the first wife, and then 2 boys. She passed away 9 years ago, and now I have a new relationship. She's sitting in the back there, Francie. We've been together for 7 years. So that's kind of more or less my life up to this point, I guess. Thank you. Yes, any other questions? Yeah. Let's see, I think she had one first.
So I grew up in North Dakota, and we saw all these, missile sites around. Did they just pull out the old Minuteman 1, Minuteman 2, and put Minuteman 3 in the same structures?
Yes, essentially yes. But there is an interesting book that I reference in my book called The Missile Next Door. So it talks about the societal impacts of having a missile on your property, basically, or next to your property. So you might be interested in that. Yes.
So when they pull a missile out of the silo and test it,
Yeah.
do they have a warehouse full of these things so that they can put a new one down into the silo?
There's 400 out there right now. There's 50 spare ones, okay, that are there, so they could use them for a while. Yeah. And they're all upgradable from a single warhead, the Mark 12A warhead, to triple, the MIRV capability. Yes?
When you wrote your code originally, how did you know that it was accurate?
We didn't. We didn't. And that's an excellent question. If you've used Windows or any other piece of software, you know it can have errors. So management in the Air Force asks me constantly, does this thing accurately represent the flight of a Minuteman III under all conditions of flight? And I just said, I don't know, we did our best. That's all I could come up with. But what they did do before the operational software was deployed, the operational flight program, is TRW, the company that made the reference trajectory, they made 5 sample reference trajectories that sort of explored the envelope of capabilities of the missile. And then those 5 were simulated with the flight program. And the rocket succeeded in all 5, so they said, well, okay, it must work. But after I left Autonetics, I understood, and I don't have anything to prove this, but that Autonetics sent the Minuteman flight simulator to a company in San Pedro, California, which spent a year analyzing it. Then it went to IBM Federal Systems Division in LA, where it spent some time. And then it went to a university in Utah, where 2 graduate students analyzed it. And the conclusion was that it worked. But I don't have a proof of that. Yeah. There's one back there.
What fuel did
did you use for your beginning rockets?
Oh yeah, we used gunpowder basically to start with.
Did you add powdered aluminum?
We did not add powdered aluminum, but in the early days we happened to read a Scientific American amateur physics article in Scientific American magazine, where a group in California had launched some rockets using zinc sulfur propellant. Okay, and so we switched everything to zinc sulfur at that point, and that worked pretty well. And so, and
Did you ignite it with a fuse?
we had an electrical ignition. We stood far away from the rocket and behind a wooden barrier and so forth. So yeah, so nobody, we didn't get hurt, and nothing really blew up. I mean, the rockets blew up, but none of us were hurt. So at the peak, we had about 8 or 10 of us in our propulsion research group. We wrote letters to the government. It was the start of the International Geophysical Year at that time. So we got tons of literature back from Washington that helped out a lot. So, yeah. Well, I think we should probably let people go. And I'll be over at the table if anybody wants. I'll sign a book for you.
Yeah, so we're gonna give Ralph a few more minutes, but yeah.